Thermal dispersion has become a popular gas mass flow measurement technology in the water and wastewater industries. Municipal end users, engineering consultants, and contractors specify this technology due to its effective, reliable performance in low flow conditions, wide turndown, ease of maintenance, and ability to directly measure mass flow without the added cost of temperature or pressure instruments and flow computers. Wet gas, which is any moisture or condensate in the gas stream, can become a costly, frustrating measurement challenge. Next up, we are going to hear a few different strategies to make accurate, reliable mass flow measurements in common municipal applications. And here to tell us more about it is a welcome guest back to the Virtual Water Expo. We love having him here. He is Adam Schlehan. He is the Director of Sales, Vice President of Sales, and the man when it comes to knowledge in this part of the industry. Adam, I'm going to hand this over to you. Go ahead and take us away.
Travis, you are a living legend. Thank you so much for that great introduction. A lot to live up to after that, and great explanation of thermal. So to introduce myself, I am Adam Schlehan, the Director of Sales here at Fluid Components International. And the issue that we're going to talk about today are the challenges that arise from measuring in wet gas applications. And those are very common in municipal. Before we get into that, just a little bit of background about Fluid Components International. We have the global largest installed base of thermal mass flow measurement equipment. We've been in business. We are now in our 60th year of operation. So that is decades upon decades of supporting hundreds of different municipal projects. One thing I would say about our thermal mass flow meters and our switches is the continuous operating life. We used to name our instruments after the year that they were made. So the FR72, the GF90, the MT86, all the years that our instruments were made in. And it is not uncommon for our salespeople to go into plants and see instruments that were installed literally in the 80s with 30 plus years of continuous operating life. The other thing that I would point out there is that supporting hundreds and hundreds of municipal projects over this time, our engineers, our sales channel, so our manufacturers representatives, and our field service team, they've developed quite the expertise as far as the municipal applications, common municipal measurements that need to be made, and solving frustrating problems like wet gas that I'm going to talk about today. So there's FCI in particular. I would say that the thermal mass flow measurement in general, regardless of the manufacturer, has become a very popular option in the municipal industry. You think of those bread and butter applications that were used in municipal, your aeration, your anaerobic digesters, anything that has to do with biogas, natural gas, combined heat and power, flares, odor control. The application list goes on. Customers, engineers, consultants like to specify thermal in general because, as Travis pointed out, it does give a direct mass flow measurement without compensating instruments for pressure, temperature, flow computers, has a very good, reliable performance in low flow and a wide turn down range. The standard of that is 100 to 1, but with special calibration techniques can go as high as 1,000 to 1. There's no pressure drop. There are no moving parts with thermal instrumentation that could clog up or foul. Easy to install and easy to maintain. And the price point of thermal compared to some of the alternative technologies is quite competitive. So thermal has become a very popular option in municipal in particular. Now, before we could discuss wet gas and the frustrating problems that it causes and how to approach them, you need to understand just a bit about our theory of operation and how thermal dispersion works. So what you see here are two photos of our instruments. The flow meter on the left is our insertion instrument, and that is for line sizes 2 inches and above. The instrument that you see on the right is our inline, and well, that's for line sizes 2 inches and below. The main concept that we have is we have two thermal wells on our sensor head, and within each of those thermal wells are platinum plated PT1000 RTDs measuring temperature. Within one of those thermal wells, we bring extra heat to the RTD, and that is called our active sensor. And the other one, there's no heat brought to that. That one's just measuring the temperature of the media as it flows by. That's our reference sensor. So two RTDs, an active sensor with heat, and a reference sensor. And at any given point in time, there is a difference in temperature between those two RTDs, and that is our measurement signal. Now, moving on to how it works in particular, is that the concept is all about the molecules. It's all about the molecules. So on the left, you see our sensing element. The red is the heated sensor. You have your unheated sensor, and then that delta T represents the difference in temperature. On the right, you see a little bit more dense of a situation. And each one of those dots there is a molecule of the gas that we're measuring. Now, that could be biogas, it could be compressed air, it could be hydrogen, it could be a blend of a lot of different things. And each one of those molecules that is hitting that sensor head has its own unique cooling effect and is taking away heat. Now, the more of those molecules that hit the sensor head, the more heat will be taken away. And the velocity, the faster that those are moving, the more heat will be taken away. This is the central component of how we work. You have the cross-sectional area of the pipe. You have the density or the pressure, which is how many of those molecules are hitting the sensor head and taking away heat, times your velocity. How fast are they moving and how fast are they taking away heat? There is a direct correlation between that difference in temperature and the mass flow of the media. Now, because our theory of operation works this way, and looking at the formula for mass flow and how you get to mass flow, which I would say is your density times your velocity times the cross-sectional area of the pipe is the mass flow. And given that we're measuring off of the cooling effect of the media being measured, there is no need for additional compensation for either pressure or temperature or a flow computer. As we said, it's the mass flow, the number of molecules that are hitting the sensor head is how we make our mass flow measurement. So with that, no need for a pressure instrument, no need for a temperature instrument, and no need for a flow computer. Now, as I said, there is quite a bit of upside to using thermal in general in quite a few of the different municipal applications. But one frustrating and expensive challenge that is commonly faced is measuring wet gas. So this is gas with moisture entrained in the gas flow. That's condensation that builds up and droplets that can come into effect with the sensing element. So what does that do? As we talked about, the thermal theory of operation, we're all about the cooling properties of the media and heat transfer and taking heat and reducing that delta T between the heated sensor and the active sensor. And in those applications, like the digesters, very, very common with wet gas, where you have the moisture and the condensation that builds up, you could get moisture that drips down the probe and comes into contact with the sensing element. And when it gets wet like that, that would cause the measurement to spike unexpectedly, and that would really throw off your accuracy. So if you look on the right here, just as an example with a graph, you have on the y-axis your flow rate, that's our measurement, and on the x-axis you have time. Now you have dry, and you see that line is very, very stable within that plus or minus 2% tolerance. And then in this scenario, we introduced mist for 120 seconds. And you'll see with that red line, the measurement, it jumps way up. Now the mass flow rate, the velocity, none of those other variables have changed, but it's that moisture and condensation and droplets coming into contact with the sensing head that spike the measurement and cause frustrating and expensive measurement issues, keeping us from getting a stable and accurate measurement. Now, as I said before, this is very, very common, particularly with the anaerobic digesters and in the municipal applications. The typical call that we get is we have a thermal mass flow meter. It's in a slightly wet gas application, and we just simply can't make an accurate measurement here. So this is routine for us. We see it all the time in this industry. And what I would like to speak about today are just good practical measures that anyone can take to get a good, accurate, reliable measurement in a wet gas application. So the three focus areas, or the three recommendations that I have just in this short time here. Number one, use a gas dryer, use knockout drums, use insulated piping. Install those upstream from where you're making a measurement. That'll knock out quite a bit of the moisture and make the overall environment more conducive to an accurate measurement. Number two, in scenarios where moist gas condensation, where that's still present, we have a couple of techniques that are pretty straightforward as far as optimized installation. And there are certain manufacturers, FCI being one of them, that do offer mechanical options to help get an accurate measurement in wet gas applications. So I'll talk about the first one. The first one that we have is that optimal installation. And the rule of thumb that I always communicate is install in a way that you make gravity your friend. So on the left, you see a picture of a sensing element with a water drop. And in many cases, that's a teardrop if you want to have an accurate measurement. And the goal is to keep those droplets and to keep the moisture from coming into contact with the sensor head. Now on the right, we have a diagram here that you see gravity is pulling those droplets down in that thumbs down scenario right onto the sensor head, and that thing is going to spike. You're not going to get an accurate measurement. That is an easy way to prevent a problem. What you see in the two thumbs up options are a 90-degree installation and a 45-degree installation. And where you would have had droplets of moisture being pulled down by gravity, that is simply no longer an easy allowing a droplet or moisture to come into contact with the sensor head. So let gravity be your friend in moist applications. It is not a best practice to install a flow meter at 12 o'clock directly down into the mass flow. Install it at 90, install it at 45, let gravity be your friend. Now in practice, here are some great examples. I saw both of these and I smiled. You'll see on the left that we came in at 90 degrees, making us therefore less at risk for having our accuracy thrown off. And the cool thing about that picture on the left is that in this digester application, there's a walkway, and the technician can now see the flow meter and the display on that flow meter right at 45 degrees without needing to turn his head at an awkward angle. So note the 45 degree rotation for easy viewing by folks who are working that facility. On the right, we're installed right at that 45 degree angle and making gravity our friend. The thing I would point out there is there's use of a ball valve and a packing gland, which makes it very, very easy for anybody in the facility to take the meter out of installation, to take it out of the process, to clean it, to maintain it, and to install it right back in with the quarter turn of a valve. Moving forward to our other option, and that is the wet gas sensing element that some manufacturers, FCI being the primary one and the only one, is use of a wet gas sensing element. And what that looks like is what you see right here in that top picture, where you have the two RTDs, and then on the other side of the sensing element, on the inlet, in a digester type application, you have a metallic shroud there that will work to shunt moisture away from the sensing element and not let the moisture spike your reading. So how does that work? Well, the gas with droplets, it comes in, that wet gas head, that mesh screen will shunt the moisture away. There is a small vent here. If you look on the bottom picture there, the water will vent out of that, and you're able to make a nice dry measurement of the media without being thrown off. So we're going to go back to this graph on the right, which shows the red line, which is what happens to a measurement without a wet gas head with mist flowing for 120 seconds, compared to that blue line on the bottom that shows what happens to our measurement when we have 2 minutes of a mist flow test. So in practice, we could look at a graph. I think that if a picture says 1,000 words, a video says maybe 10,000 words. We do have a video here that we'd like to show. So here's a video. We have a mist that we're introducing to our gas flow stream. We have our flow meter installed at the proper 45-degree angle here, and you can see the readings as the mist goes up. You can see that we are stable. We are within that plus or minus 2% of tolerance, and that you don't have big, massive spikes in the reading. So in practice, in reality, the mesh screen, the wet gas sensor shunts moisture away and allows for a good, stable, accurate reading where you might be thrown off if you're not using this as an option. And one thing that we hear and that we see in industry is operators might ask us, well, what about using high levels of heat and really heating the device to a temperature that would flash off moisture? We've seen this out there. This is not an option that we have decided to take, and it is not an option that we recommend. What it typically looks like is you will have the device heated up to 300 degrees Celsius or 572 Fahrenheit to flash off the moisture. We have not opted to take this approach. For one, we are concerned that it could create an unsafe working condition. For two, it consumes a lot of energy to operate the instrument. And all that heat, if you think about the electronics in the instrument, we worry that it would shorten the operating life, and it would prematurely age the instrument and make it susceptible to drift. So the high heat, not something that we advise. Moving forward, this is all I have for today. The things that I would ask for those who are interested in learning more. Number one, get in touch with our sales channel partners. Our channel partners are in-depth experts in municipal. They don't just carry thermal mass flow, they carry other technologies that are widely used in the municipal and the water and wastewater markets. Number two, come to our website. We have a wet gas measurement guide on our website. We have several application handbooks. We have a wastewater and water applications guide. Finally, come check us out on LinkedIn. And anyone who wants to learn more, please feel free to get in touch with me. Please feel free to get in touch with our reps. And Travis, thank you very much for my time here today.
Always good to have you here, Adam. There's a lot of good information there. Thank you very much for joining us once again here at the Virtual Water Expo. And yes, there's the contact information right on the screen there. You can always find FCI prominently displayed on Water Online as well. Adam, you are an expert in this part of the industry. We appreciate your time. I'm sure our users do, and I cannot wait to have you back for the next one. Adam Schlehan, thank you very much for joining us today.
Thank you, Travis.